Hello guys, so this is a video I have been very excited about. We are talking about calculus. So what's this video going to cover? Well, everything. This is the final video in the series and we are done with maths methods. Potentially in the future I will do the spec course, but I would like to see some more interest in the channel. I'm potentially going to try some new videos that aren't related to maths before I go back and do the spec course. Now, what is this video going to cover? Rates of change of nonlinear functions, slope of a chord, first principles, derivative of a function and derivative of a point, derivative of x raised to the n, addition and scalar properties, derivative of polynomials, slope of a tangent, displacement and velocity, increasing and decreasing functions, maxima and minima, local and global and stationary points, and optimization. Rates of change. Calculus studies rates of change. A rate of change is a ratio of change in a quantity due to a change in another quantity. A common example of this would be that a rate of change in distance in relation to speed to time is speed. If you move 5 meters over 1 second, you have a speed of 5 meters per second. Let us consider the function fx equals x. Now the rate of change of fx is in relation to x is 1 because for every increase of x, there is an equal increase in fx. The rate of change in a linear function can be easily found using the rise over run function as change in y over change in x. How would we solve the rate of change for a nonlinear function? What we need to do is solve the rate of change at a point. However, this is impossible. How do you solve the simultaneous rate of change at a single point in time? The similarly impossible question is not solvable, but we can try approximating what this value would be if it was possible. What we can do instead of finding the instantaneous rate of change is find the gradient of the curve at the point. This is done with first principles. So as you can see, we are approximating the gradient of the curve as this distance approaches 0, but is not 0 because that would be impossible. So it's the gradient as the distance between these points approaches 0. There we go. This is the equation. So the function of fa plus h, take fa over h, is the limit of h as h approaches 0. That is how we define the derivative. So let us solve this question here. We are going to consider fx equals x squared. Now we have f dash x equals lim h approaches 0, fa plus h, take fa over h, and you substitute it in. What you're going to find is that the derivative of x squared is 2x when you use these limits. Now the derivative at x equals 0 must be solved. At x equals 2 must be solved. So what is the derivative at x equals 2? And then, well, we know that the derivative of fx is 2x, so we can just put that 2 in and get 4. The derivative of xn. Now, consider this equation here. We're putting in our xn using first principles. And what we find is that it is n x n take 1. So you need to remember this. This is very important. Write this proof down just to get more familiar with how these proofs are done. All right. But basically, you're going to want to memorize this because you don't want to do first principles all the time. You're basically only going to have to do it now and a little bit in year 12. Addition and scalar properties. The addition property is, if you've got fx plus gx and you take the derivative of that, that'll be the derivative of fx plus the derivative of gx. And the scalar property is c multiplied by fx, take the derivative, equals c multiplied by fx derivative. So it doesn't matter where you put the c. I would like you to attempt the first principles proof yourself. They will be almost identical to the proof for xn. So I would like you to try and get this function here and prove that it equals this using first principles. Here's an example of applied calculus. You can solve the derivative of this polynomial using first principles, or in this case, you could use that the derivative of x raised to the n is n x raised to n take 1. You don't need to do it in first principles. Find the slope of the tangent. So if we want to find the slope of the tangent of this, we need to solve the derivative, and we want to find the slope at 10. Well, the slope at 10 is going to be this. Easy peasy. A function is increasing if the derivative is greater than 0, and it is decreasing if the derivative is less than 0. The derivative of displacement is velocity, and the derivative of velocity is acceleration. Consider a negatively charged particle moving at some speed. It is moving away from a positively charged rod, which is applying an acceleration of 5 meters per second on it. So displacement is 10 meters. We know that the acceleration is -5, since we sub it in here and we're using -5. And then we can rearrange this equation in terms of t and get that the velocity is this. Optimize. When f dash x equals 0, this means that the tangent is horizontal. This corresponds to a critical point. This critical point could either be a local maximum or minimum, or a stationary point of inflection, a point with a horizontal tangent that is not a max or min. It can be determined whether a point is a max or min by testing values which are slightly higher or lower than the value of the critical point. Optimization is the act of finding the most efficient method of doing some task. This is often achieved by finding the max or min of some function. And here is an example. So we want to maximize the area. So area equals length times width times height. All right. The box is defined by a length of 5, a width of 3 take x, and a height of x. So what is the max area? Well, we're going to find the derivative of this function here. There we go, rearrange it, x equals 3/2 as a critical point. Now I will allow you to experiment because a critical point could be stationary, it could be max, or it could be min. But you'll find that it is the max. You can just look on your calculator if you want to be sure. And there you go, you plug it in and that is the maximum area. Well, thank you for watching. That was the last video in the series on maths methods. Please like, comment, and subscribe. There will be more in this space. There will be more in this space quicker if I get more positive feedback and there is more interest shown, then I will make this my top priority. But for now, I just want to say thank you for watching and thanks for going on this journey with me. I really, really hope this has helped you with your studies and will help you excel in year 11 and in all your future endeavors. Thank you very much and good luck.